So this is our second day session. So here, so we all know that many students find maths difficult, especially the calculus, and the students are struggling to understand the concept of calculus. Mainly the reason I would say that we are just like that giving our formula and telling them to learn and by heart and apply that. That may be one of the reason I would say. So that interest in the children is losing here by and large. So our responsibility is to tell the children that it is an intermediate only. That calculus is actually an intermediate max only. There are more abstract concepts in mathematics which is even more difficult than this one to understand. So actually a preparedness to learn the calculus is very important. Preparedness, when I'm saying, maybe this situation would help you to understand. Maybe a father tells a child that before you learn cycling, you will definitely fall 20 times. If he says that statement first itself, probably the child will not find it difficult if he falls down one time, or the second time also he will not feel bad. He will get up immediately and again he will start doing that. Okay, so maybe 2 3 times he falls down, he will not find it hard, isn't it? So maybe a sixth time he falls down and he will learn the cycling, and he will be in fact happy with his achievement. Okay, my father has told 20 times minimum you will fall down to before you learn cycling, but I could learn the cycling by the sixth time itself. Okay, so the kind of preparedness to the mind before we learn the calculus is very important. So here, if you really give the concept of calculus, just like algebra and the trigonometry, they will also try to apply that in the real life situation. So it is very important for us to say what is calculus all about. So definitely we all know that how the arithmetic is evolved in the history. If you look at the history of mathematics, maybe because of the trading. Okay, they wanted to do the trading, they wanted to do the arithmetic addition, subtraction about the goods they wanted to. So it is purely out of necessity that arithmetic or the algebra is evolved. So what would have led to this calculus? What would have led to the this development of calculus would have really happened? So children would be really interesting to know all these things. So if you look at the history of mathematics a little bit, we will also get some idea about that one. It's very important. Before we start the chapter, we have to give some idea about the history of calculus. So we all know that the ancient Greeks were the reason to understand the shapes and the characteristics. So they figured out how to find the area of a polygon by splitting that into triangles. Okay, how to split that into many, because many vertices we have. So they know how to divide this into many triangles, and they could easily calculate the area of the triangle. And again, they trouble came when they actually started giving the number of sides. If the number of sides is increased, then also they are able to divide into triangles, not only hexagon, any number of polygon, it is possible. So the trouble came when they actually had to calculate the area of the circle, because the side doesn't have any vertex at all to join two vertices to form a triangle, isn't it? So a method called method of exhaustion is developed by Greek. It is nothing but they introduced inscribed a lot of shapes inside the triangle. So they begin with the triangle three-sided, and then they increase the number of sides of that polygon which they inscribed inside the circle. Then 4, then 5, then 6, then 7, etc. They increased the number of sides of the polygon inside the circle, and this method is what we call it as a method of exhaustion. And finally, they come to the conclusion that inside that whatever is inscribed is looking more and more closer to the circle. So they identified that they need a polygon which has infinite sides to get a closer area, closer to the area of the circle. Okay, so even then, if it is never equal. We all know that it is never be equal. So, but more and more closer to the area of the circle. So, in fact, the Greek couldn't actually identify the concept of this limit, but even then they could identify the formula as pi. They arrived at a conclusion. There exists a constant called a pi. Okay, they didn't get the idea of the limit at that time. Okay, so here we in order to find the area of this curved shapes, we need actually a more sophisticated method, because whatever we have in our system, it will not work in this kind of curved diagrams. So if it's a rectangle, if we are taking, there will be the opposite sides, two opposite sides. If we take the height is the same, whereas these kind of diagrams will have from A to B, if we are taking, the length is not same, the vertical distance is not same. So exactly those idea which the Greek people have identified, that method only we are actually using in the calculus. So similar methods, we have to say similar methods we are using. So area can be approximated by using the rectangles. Okay, so more and more rectangles if you bring inside, the more and more approximation to the required area we will get. So that infinitely many rectangles we have to inscribe to get a precise area of that one. Okay, so rectangle was easy, whereas this kind of diagram we need a curvature diagram, irregular dimensions. In order to find the area, a new technique is needed, and that new technique is developed by, started with the Pierre de Fermat, and again the Newton, and then again Leibniz. These are all the people who contributed. In fact, what we learned today, the notations, everything is the findings of Leibniz. Okay, and Newton, of course, identified the rate of change of the positions. Okay, so because of these people, so here again the necessity of the Newton to calculate the movement of the celestial bodies. Okay, he actually wanted to identify the in order to understand the rate of change of the positions of the celestial bodies, he wanted an idea, a sophisticated idea. In fact, Leibniz also found out the same idea after a few years. Okay, after a few years, the same idea is used by him, which the notations we are using today. So what Newton observed is the falling objects, okay, realized that each and every moment the speed of the object is changing, in fact increasing, okay, at every moment until it reaches the ground. So during at that instant, the object must have some definite speed. So he realized the need for the new technique, which we call the rate of change of the position or the velocity. In physics, in detail, they are studying all these things. So in a way, the rate of change problems developed the idea of the differential calculus, and the area under the curve problems helped to evolve the concept called integral calculus. Both these differential, whether it is differential or the integral calculus, this has something common in this one. That is, we can do something infinitely many times to get a finite answer. That concept is there common in both this one. To get a finite answer, we have to do certain things infinitely many times, isn't it? So until the 17th century, what they couldn't find out by the Greek, these people have identified and found out. There is something called Zenon's paradox. So that paradox says that a man, if he wants to touch the wall, okay, he has to travel first the half distance of the total distance, and then again the next half he will divide again into one more half. The next half again he will divide into one more half, and he has to travel and calculate the time. And if he continues this one, the concept is that he can never touch the wall, because that will be divided into half until it reaches the wall. But we all know that the man can touch the wall. So here also the concept is infinitely many times that particular thing is done, but we are getting a finite answer. Okay, so this is the whole basic idea of the calculus. In fact, this led to this led to the development of some infinite series called E. Okay, we all know the value of E and all, we would have told our children, but how that infinite series came into effect, we never told our children. We would not have, even I didn't say that, but these are all the infinite series, which when we try to calculate, we get a finite answer. Okay, so this is the whole idea of the calculus. So something we have to do infinitely many times to get an answer. So limit of infinity, or at the end of infinity, we get a conclusion. So if we give some kind of ideas like this, okay, initial ideas like this, we can definitely bring the curiosity in the minds of the children, and we can definitely make them understand this is the reason why we are learning all these things. Okay, these are all the development in the history. We also can contribute a lot of things if we think like that. So these are all some of the ideas. Okay, so here the differentiation, the formula as such, if you are giving the formula like this one, definition, if you start going and writing on the board, suppose f is a real valued function on the subset of the real numbers at the point C, this is the definition, probably they won't understand anything. This is very abstract to get the meaning of this one. Okay, so we will try to give a meaning to that one. Okay, this is just a trial from my side. Okay, probably we can introduce, or we can ask the children to find out the equation of the tangent line at a given curve y is equal to f of x at a point a comma b. So when we ask them to find the equation of the tangent, let me put it in the slideshow mode, 1 second. Okay, so tangent line, they have already learned the idea of the straight lines in class 11. So they will give you the suggestions like, okay, to find the equation of the straight line, isn't it? They need y equal to mx plus c formula to apply, or a 2-point formula to apply. These kind of ideas we will get from them. So y equal to x square is a very good graph in order to explain that. So I am just taking one point. I'm trying to tell the children, okay, to find the equation of the tangent at the point 1, 1. So y equal to mx plus c has two unknowns, m and c. We need two dimensions to find the equation of the tangent. Otherwise, if it is a 2-point formula also, we need 2 points to find out the equation of the tangent. So we can ask them, how can we find out the straight line equation here? Okay, so let us give some idea like we can find or assume one more point on the graph. And the particularity of this graph is all the points is in the form of x comma x square, isn't it? Because it's a graph of y is equal to x square. So 2 points we are getting. So if you join these 2 points, we get a secant line. We get a secant line. And their children already have the idea how to find the slope of this particular line using slope point form y2 minus y1 is equal to x2 minus x1. Let us bring that idea from them. Okay, and we will try to help them to find out the slope of this secant line. Okay, using the formula x square minus 1 divided by x plus 1. This can be actually simplified. It is in the form of x plus 1. If you simplify this expression, x plus 1 you will get. So let us allow the children to find out the slope starting from 2. Okay, starting from point right side from 2 and left side from 0. Because I am trying to find the tangent equation at the point x is equal to 1. So let us try to give some values to this one. From 2, if they start writing, what will be the slope? We can ask them. So let them write, okay, substituting in this one, let them find out the values. Okay, so they will get the answer as 2. Again, let us try to give the next nearest point. Okay, again, let us help them to find out more and more closer to 1 values. So they will understand here that finally the slope value m is approaching to the number 2. They themselves can find out that. That is from the right side if you are approaching. Similarly, from the left side also, let us encourage the children to find out the values. So from starting from 0, 0.5, 0.9, what is the value? Okay, and slowly they will approach the number 2 here. So finally, they will get a conclusion. Okay, slope of the tangent at that point 1, 1 is 2. And that will in turn will help them to find the equation of the tangent line. So here that point 1, 1, if you substitute, you can find out that a b value also here, y equal to mx plus b I have taken. So that value also we can find out, and hence we will be getting the equation of the tangent y is equal to 2x minus 1. So here at this point you can tell, okay, we have applied the idea of the calculus or the rate of change of idea to find out the slope here. Okay, and in turn to find out the tangent equation. Okay, sorry. So here, now if you tell them the equation, the definition of the differentiation, probably they can understand this very well, because this is nothing but change in that x value, isn't it? Small x value, a small change is given here. This is that x value before change is nothing but y2 minus y1. And here it is, if I add a c and subtract a c, this is nothing but x2 minus x1. So this is nothing but the slope formula only. At a very small instant, what is the slope you are trying to find out? If you convey this message, okay, then they will understand the meaning of the differentiation probably in a better way. And right side, when they are approaching, we call that as left differential coefficient, isn't it? Left differential coefficient. And from the from the right side it is right differential coefficient, from left side it is left differential coefficient. Like that we can introduce that a limit will exist when only when both the values are equal. So in this way, if you bring the concept of differentiation, probably they can understand in a better way. Now, again, if you start explaining about the continuity after that, it will be easy, because the graph should definitely be continuous in order to find out a tangent. In order to further, should exist one point and then only you can draw a tangent. So continuity is something which is very, very necessary. That idea we can bring in their mind. Okay, and now if you introduce the concept of continuity, probably they will understand. So here I have explained the, in order to explain the formula continuity, I have given 3 situations here. This is just my way of giving the idea in the classroom. Okay, you can also share after this session. So here there are 3 points of discontinuity: x is equal to a, x equal to b, and at x is equal to c. So we all know that this whole circle means that part of the point is not the point on the circle, isn't it? So here, if you try to find out the limit at these points, limit concept, the understanding is that limit concept they already know. Okay, so limit extends to, from left side, if they approach, okay, the function y is equal to f of x approaches to the number L1, they themselves can say that it approaches to the number L1. Okay, and from right side, if it is approaching to the number a, that we mention like this, limit extends to a plus f of x, that will be, the function will be approaching to the number L1 itself. And if you ask the question again, the here left limit is equal to the right limit exists, even then we have a discontinuity there. So we can ask them, what is the reason why there is a discontinuity here? So the problem is because of this break here. Why that break came? Because the point a comma f of a is not defined there. That is why I could not plot that point there, and I couldn't join that line here. So it is very important that the f of a is well defined here. Then only the graph will become continuous, isn't it? Similarly, the second point, if we take at x is equal to b, what is the situation? Why we have a break there? So if you look at that one, from left side, if we are approaching, limit extends to b minus f of x, the graph is approaching to the number L2. So here I have marked L2. It is approaching to L2, and limit extends to b plus. From the right side means here it is, there is a point here I have marked L3. F of x is equal to L3. So here definitely the limit doesn't exist. The children themselves will say the left limit not equal to the right limit, and so the limit does not exist. That is the reason. Actually, there is a jump here. We call this kind of discontinuity as there is a jump in the graph. Okay, and this is a not removable discontinuity, whereas the first one is a removable discontinuity. We can define that function at that particular point x is equal to a. We can join here. It's called a removable one, whereas this is not a removable discontinuity. And the reason for the third one, there from the left side, the value is approaching to L4. Right side also, the value is approaching to L4. And at the point C comma f of c exists here. So all these happened, even then it is not continuous here. The reason is what? Limit extends to c minus f of x exists. Limit extends to c plus f of x exists. Both the values are equal to L4 here. Both the values are L4. But what happened? F of c is L5. These two are not equal. So this idea, if you give them, they will understand. Okay, limit extends to, in order to, at a point A, if we have to check the continuity, limit extends to a minus f of x should be equal to limit extends to a plus f of x, and that should be very well defined at that point. It must be equal to f of a. Now, if you look at this one and encourage them to always check these three cases whenever they write down the problems, and they will clearly follow that. So first to find out f of a. First, then check the limit, left limit, then check the right limit, check whether all three are equal. If you give that idea, probably they will grasp that in a better way. After introducing all these concepts very clearly, we can give all the formula, perhaps starting with the polynomial functions. For example, x cube, what is the, now x square we found out, the derivative is 2x, x cube derivative is 3x square, x power 4. So a pattern they will try to understand from this one, and finally they can understand x to the power n. It is nx to the power n minus 1, and then you also first principle method you teach them. What I'm saying, trying to tell is more than one method is needed to give a clear picture of what we are trying to tell. What is the derivative of x to the power n? More than one method is needed. Okay, and then you bring the idea sin x derivative is equal to cos x. Here, I would like to show my GeoGebra applet also to find out the derivative of sin x. Okay. So here is the graph of sin x. Can you all see the screen?
Yes, ma'am.
Yeah. So this is the graph of sin x. Okay. So how to do this applet and all, we will see later. Let us try to understand how can we show these things, visualization. Okay. So here I have selected one point on this graph. So whenever I move this one, that point will also move. Are you able to see the point here? The point will also move here.
Yes, ma'am.
The point A, isn't it? So
Yes.
when I'm moving, the point A is also moving. So I'm trying to find out the tangent at that particular point A. So if I draw the tangent at that point, if I am trying to move this one, the tangent will also move. Okay, the tangent will also move here like this. Okay. And now I'm trying to find the slope of the tangent. Okay, this is a very good example to get the picture of where the slope is decreasing. See here, it is a negative slope here. F dash x is lesser than 0. Okay, if it is coming to this position, okay, that is at this position, that where a horizontal tangent exists. Okay. Exact point I'm not getting. I'm sorry. 1 second. So here, when it crossing, you will understand the slope is 0, and I'm not getting the exact point. So here the slope will become 0 because it has a horizontal tangent at that particular point. And this side, this way, it is the slope is increasing. The positive slope we can observe here. Okay, and then all these increasing, decreasing idea, maximum, minimum idea, everything we can explain with this graph. Okay, and then if you try to plot whatever we are getting the slope, okay, we try to plot this point P. P is actually the slope corresponding to this point, the movement of A. And if I try to trace this one, you see what we are getting. Okay, I'm trying to trace that point. That is the tangent slope I am trying to trace. So what we will get the answer? The
Cos X.
curve will be cos x curve, isn't it? That curve will be the graph of cos x, isn't it? So in this way, we can also give some more clarity to the idea that the derivative of sin x is cos x. Any graph, any polynomial function also we can show this way. Okay. Is this clear, teachers? Anything to tell here? Hello?
Clear, ma'am. It's clear.
Yeah. And similarly, I will show here how to, 1 second. The one point of discontinuity also we can show here. Okay. Non-differentiable case. So this is the graph of a non-differentiable case. So what is happening at this particular point? Okay, when the tangent line is moving. So here and all, the slope is movement, slope value changes, we can tell them to observe. Here you see the slope is positive at this particular point. If it crosses that point also, the slope is here positive itself. That point is a point of inflection, isn't it? Because to the left side and to the right side of that point, slope is not changing, it's a sign, isn't it? So it is neither a maximum nor a minimum point. We can tell that it's a point of inflection, isn't it? And the point slope is m, the slope m value is increasing here. And if it touches at that particular point A, you see here what is happening. You will not get a unique tangent, or the slope will be different at that particular point. You will get a 2 slope at that particular point, m equal to 3 and m1 is equal to -3. That is left value, left side value will be 3, right side, if you calculate the differential coefficient, the value will be -3 you will get. So that is the reason why we say here it is not differentiable at that particular point. Left differential coefficient not equal to the right differential coefficient. So that idea we can bring here. And here again, if you move this curve, you can understand the slope is moving, is increasing, slowly decreasing here, and then again increasing here. Okay, so this is the minimum point. We can say the local minimum idea and all we can discuss here, isn't it? This is a very good graph to explain all the points here. This is a point of inflection. This is a non-differentiable point, and this is a point where the minimum, local minimum occurs. So all these ideas we can bring, and then you explain the formula of that one. Probably they will even that visualization will be there in their mind to understand that concept. Okay. So I'm coming back to, so after giving all these ideas, probably now you can give a playway method. Okay, give a lot of worksheets, lot of playway methods to strengthen that formula in their mind. Okay, so this is one such worksheet where they can play with this one. This is nothing. If we horizontally or diagonally or any vertically, any method, anybody who first find out all the correct answers in line, they will be the winner. Like that, some playway methods you can bring in order to strengthen the ideas. So these are all what we usually do. So here is some questions to discuss. Okay. So here, as I said earlier, we can always tell them to write the formula in the examination point of view. Okay, that is limit x tends to 0 minus f of x is equal to limit x tends to 0 plus f of x is equal to the function value at that particular point. So we can also say, okay, it carries some marks. So here f of 0, immediately they can identify from the question the value is equal to -1. Then we will start finding. So in this kind of question, I will suggest the H method is more useful. Okay, H method of differentiation in order to calculate the left limit. So what is H method? You all know. So we are substituting x is equal to 0 minus h to calculate the left limit, that is value slightly lesser than 0. And we are substituting that in our function. So we will be getting e to the power 1 by minus h minus 1 divided by e power 1 by minus h plus 1. And we have to give them the idea that e to the power minus infinity value is 0. And e to the power infinity value is nothing but e to the power minus infinity or 1 by 0. That would be infinity. So these are all some standard values we have to give them and tell them to memorize. And so when you apply the limit here, we will be getting 0 minus 1 divided by 0 plus 1, the value left limit value equal to -1. So with this two things are equal, we cannot arrive at a conclusion. We have to tell them to calculate the right limit as well. So this is a right limit. In order to calculate the right limit, H method I'm using. X is equal to 0 plus H we are giving. So as H tends to 0, this X value will tend to 0. So e to the power 1 by H minus 1 divided by e to the power 1 by H plus 1. So what is happening here? When you apply the limit, again, we are getting an indeterminate form here. Infinity by infinity we are getting. So we need to do some more changes in the question that we have to say. That indeterminate form we have to remove. So we can, what we can do here is e to the power 1 by h we can take outside and help them to understand that once if you take that outside, it will become e to the power minus infinity when they apply the limit. So in that way, we can bring this ideas. This e power 1 by h will get cancelled. And when you apply now, this quantity becomes 0, tends to 0. And so 1 divided by 1 is the answer. So here, these two values are not equal. So limit doesn't exist is the reason. Limit x tends to 0, f of x does not exist here. Or by chance, if they are writing the right differential coefficient first itself, and they are able to say these two are not equal, that is also fine, isn't it, sir? They can stop, right? They don't have to calculate the left limit in that case, isn't it? They can arrive at a conclusion if they are calculating the right limit first itself.
Yeah, not necessary, madam.
Not necessary. In case they are doing the left hand limit first, and then it happened to be equal, and they are checking this one. So depends upon how they are proceeding. So is there any anything to share on this question?
So instead of doing that, e power x, limit x tends to 0, e power x minus 1 by x, which is equal to, I think, 1, madam. There is a standard limit, no? Already we have in 11th standard, I think. Exponential functions, the limit of exponential functions.
But here it is e to the power 1 by x, no, sir. E to the power 1 by x.
No, the question it is e power x only.
Oh, sorry. It was my mistake.
Sorry. 1 by x.
Sorry, it was 1 by x. My typing error. I'm sorry for that.
It's okay. That's what I was confusing. Yeah.
Okay. Sorry. So this is e power 1 by x.
Yeah, okay. That's fine, madam.
Yeah. So in this way, this question is actually a board question in 2016.
Yeah,
somewhere asked.
Yeah, yes.
Yeah. Okay, so in that way, we can bring the answer. So any other views on that? Anything to share, teachers? Okay.
It's okay, ma'am.
Yeah. Now let us see another question where probably your children will also ask the doubts in the class. This is one textbook question, I think, right, sir? It's a textbook
Yes.
question only, yeah.
Yes.
The continuity, checking the continuity, and we all know that greatest integer function, we can tell them that it's all discontinuous at all integral points. So the
Yes.
question may ask as a prove that type also. So here the function f of x is equal to x minus the greatest integer value of x. Okay, and so here again left limit and right limit we have to calculate, and we have to at the point, let us assume one point first of all. At the point C or A, we are calculating the continuity. So what happens when the function at C? So greatest integer function, we have to remind them one more time, even if they have learned in class 11. So greatest integer value is the answer will be lesser than or equal to that particular number. That numerical explanations to be given. And again, if you proceed with the unknown like a C or A, they will understand in a better way. So here C minus greatest integer value C. So equal to case works here, equal to. So this is already an integer. So definitely the answer will be C minus C, and the answer will be equal to 0. And limit, right limit, if I am trying to calculate the right limit here, limit extends to C plus f of x. If I try to calculate, limit extends to C plus the first, so let me give the h method here also. So x is equal to C plus h. So as x tends to C, h will tend to 0. In that way, we can bring here. So this is limit h tends to 0. Okay, C plus h and greatest integer value C plus h. So here we can give some idea like maybe C is equal to 1, that h is a small increment 0.01, something like this. So 1.01, what will be the answer? The answer will be 1, isn't it? In that way, we can give some numerical examples here in order to bring the answer. So here as h tends to 0, this becomes C, and this value becomes C itself, because even if it's a decimal case, it will be the integral value lesser than C plus h, C minus 0, and hence you can bring the answer as 0. And as a third point, we can say limit extends to C minus f of x, and this would be limit h tends to 0. I'm calculating using h method, x is equal to C minus h. So as x tends to C, h will tend to 0. And here also the formula apply in that question. So we will be getting C minus h, and so C minus. So here a value, this value 1 minus 0.01 it is. So it would have gone slightly lesser than the number 1. And so the answer changes here. Here the answer would be one number lesser than C. That idea by numerical examples you have to bring here. And then the answer would be equal to 1. And in this way, if you proceed, we will understand that limit is not equal. So limit extends to C plus f of x not equal to limit extends to C minus f of x, and hence the function f is not continuous. In this way, we can arrive at the conclusion. And this is only one integral value we have taken. And then generalization. So it is discontinuous at all integral points, a final conclusion to be written. That sometimes children miss that idea. They will simply calculate only at one point, and that final conclusion they will not say. So that is so we have to encourage them to write that. Isn't it, sir? Isn't
Yes,
it, teachers? Any opinion on this or any different method you are trying?
just if you show the graph of the function, also we can find that it is discontinuous with all the integral values.
Yes, yes.
Easily we can understand.
So always that imagination through the graph was compulsory while teaching the calculus. Isn't it, sir? One time when
Yes,
we
ma'am.
had in I remember in one of our board exam question itself that a 9y square is equal to x cube. Find the tangent and normal. There was a lot of
Yeah, yeah.
discussion in that examination center itself, isn't it?
Yes,
We actually get a 4 points as our answer, whereas
yeah,
only the correct answer.
correct.
So if they have the idea where this curve lies, it's actually in the first quadrant and in the fourth quadrant, they will be able to choose that point clearly. So in fact, for that question, I remember in the board, they gave marks for any two, I think.
Yes,
Any two, yeah. Even if they haven't written the correct answer, we can give the marks like that board decided. But if we encourage the children to imagine the graph also side by side, okay, then definitely they will arrive at a conclusion. So this is the exact points and they can find the tangent and normal at that point. So in that way, we can bring. Okay.
yes, sir.
Any other experience your side, teachers? So here another question I have. Show that the function f of x is equal to mod x minus 1 is not differentiable. Modulus function generally not differentiable at that turning point. That idea we can generalize and give them. So here is one question. So immediately, sometimes this question asked as an objective question also. Find the points of discontinuity or find the find the point of points where it is not differentiable. How many points are there? Objective type of question also sometimes asked. So we can immediately give the idea that at all turning points, these are all not differentiable. That idea as a general answer we can give them. Isn't it, sir?
Yes, ma'am.
Okay, so we will be discussing this one. So one suggestion is that we will change the question here. Definitely we all are doing. This is just to recollect what we have, what we are doing in our class. So f of x is equal to here minus of x minus 1 when x is lesser than 1 and when it is greater than or equal to 1. That is turning point is at 1. Turning point is at 1. So that idea we have to give them. We have to allow them to think, okay, the 1 is the turning point. So to the left side of 1, if any value is substituted, and these are all they are learning in class 11, the change in the value of x, how the positions changes, how the domain changes. These are all they have learned in class 11. So the visualization would be easy. And then if you start a differentiability, the formula, of course, we have to give left differential, right differential coefficient differently, that idea. So we use the notation r of f dash of 1, r of f dash of 1. So limit h tends to 0, f of 1 plus h minus f of 1 divided by h. This formula, as well as the right limit left limit formula, we have to give. L of f dash of 1 is limit h tends to 0, f of 1 minus h minus f of 1 divided by minus h. In this way, both the formula we have to encourage them to write left differential coefficient as well as right differential coefficient, and then let them apply that. So limit h tends to 0, 1 plus h. If it is 1 plus h, it lies in this category. More than 1 it is. So they just have to replace this x value. So 1 plus h minus 1 divide, minus, this is the first term, f of 1 plus h. Then f of 1 also 1 minus 1, substituting in the place of x, the value 1. In that way, we can bring the answer. So let us encourage them to write all the steps while writing. So here we are getting H by H. Then sometimes one student of my class asked here, this is again an indeterminate form. Why we are saying the value is equal to 1? Why it is not 0 by 0? Anybody, any such experience in your class? Why this is not 0? Why it is 1? Why it is not 0 by 0? One of my student asked.
H approaches 0 means H is not equal to 0.
Not equal to 0 here.
It's
Here
approaching 0.
Approaching 0 here. So that is one confusion may be there in this case. Okay. So here actually it's an approaching value only, not exactly 0 here. H value is not exactly 0. So that is what we have to tell them, and hence the value is equal to 1 here. And similarly, the left limit while calculating, limit H tends to 0. This would be the first case. This is actually minus x plus 1, lesser than 1 case. Here we have to apply the value. So 1 minus of 1 minus h minus f of 1. Okay, 1 minus 1 divided by minus h. So here again we are getting the same type with a sign change, but minus of minus plus h divided by minus h, and so the value is equal to minus 1. So here also we can tell them that the left differential coefficient is not equal to the right differential coefficient. Okay, L of f dash of 1 not equal to R of f dash of 1, and so it is not differentiable. At the point, this is the algebraic way of writing the proof. We have already shown them how visualization of that one. It's a better before any discussion. Visualization of using graphical method is also needed. So in order to better way of understanding.
My experience, I am Mr. Kuralmani.
Yes, sir.
Yes, sir.
I feel a little bit difficult about the first exercise.
First exercise of that the continuity you are saying?
Yes, that when C is less than 0, C is greater than 0, because it takes 1 week to complete that exercise. So mostly I will teach that exercise at last only. This is where I am feeling difficulty. Apart from the first exercise, I don't have any difficulties in that.
Yeah. Yeah, that's a continuity, no, sir? Continuity exercise 5.1 you're talking about, yes.
Yes, in exam point of view also they are not asking. That except this what we discussed today, that continuous at a mod of x minus 1. That question they are asking are finding the unknown value of k. So my question is here, why we need to waste time by solving that when C is greater than 0, C is less than 0, that before that exercise, before that problems, they have given verify the continuity and discontinuity of the function.
Yeah.
Can you able to understand my question, sir?
Yeah.
First exercise, first 10 problems, I think so.
Yeah. First 10.
So how to overcome this? Any suggestions?
But the first exercise, all these are all algebraic type only, no, sir? X minus 5, 1 by x minus 5.
Yes, ma'am.
All rational functions and the polynomial functions.
Polynomial functions only, yeah.
Yeah, polynomial functions are continuous always. There is a theorem.
Yeah.
And also we have to prove that at any real number, the function is continuous. We have to show. Just we can take any real number C and then we can show that it is a continuous function. Limit A extends to, for example, at 0. So limit extends to 0 f of x. So no need of left hand derivative, right hand derivative, and then we can show like that also.
Yeah, directly we can do that.
And then, but this is a must, sir. That the exercise is a must. All each and every problem you have to work out. Then only the continuous function, every continuous function, only it is a differentiable.
Yes.
Yes, sir. For that it is needed. And then, our suggestion is better to complete that exercise. Then you go for differentiation. And then, and also, it is not the exercise is not only enough. So we have a lot of questions outside the exercise using continuity. So because the board examination, they may ask Many
previous
examples
board papers, it is better to go through a lot of questions we will get.
Previous board papers, even the 2008 paper, this is the first textbook. I don't know. I don't know the question is there or not. The first textbook, when it is printed, no, the first question paper, they asked a continuity, very tough question. I think it's a hard question. Actually, it was a hard question they asked. So that we can go a lot of, we have to give a lot of exposure to these topics, continuity. So they may ask, yeah, because it is but not only the 34 problems or 38 problems are there.
Yes.
It's not sufficient for them. We have to give extra questions.
Extra questions. Even the problems with the unknown numbers, like a small a, it is continuous at some point. Find the value of a, find the value of
fraction,
b.
The fraction, for example, 2 by x squared minus 1.
Yeah.
Whether the denominator has a polynomial term, especially given us. So last time we are discussing.
Yes, sir. Yes, sir.
That fractions.
Yeah.
Can you remain, sir?
Yeah. That suppose,
the fractions.
that
maybe polynomial is a continuity that except that number alone you explain those things.
1 by something is written means it's not a polynomial actually.
Yes.
It won't be considered as a polynomial.
It's not polynomial, but we are discussing that, ma'am.
Or is 1 by x? Sorry, simple example. You can take 1 by x.
The fraction is there.
One second.
Fractions. Okay. 1 by 2x minus 3. I don't know, ma'am. But we are discussing that problems.
Yeah.
While revision class, I think.
Yeah. You are right.
With the graph, Malika ma'am explain everything is graph. Graph we can understand that time.
Yeah.
1 by x graph. Yeah.
Yes, ma'am. I explained that. So that's only I remind you.
The 1 by x graph, it is actually it's not continuous. We can very well say that.
At x is equal to 0.
Yeah. 1 second. 1 second. So 1 by x function you are saying.
Yes,
1 by x. So this is the graph of 1 by x.
Yes.
So we can very well say the point near to 0, if the x value is more closer and closer to 0, y value is increasing to infinity. Y value is too big. Whereas left side, if it is approaching, it goes to minus infinity. So that it's actually this y-axis will act as an asymptote to the diagram. That is something which touches the graph at the infinity. It will never touch. Assumption only that it will touch at the infinity. That kind of line is called asymptotes. So here the diagrammatic view will be helpful. And theoretical algebraic view also we can work out. Shall I work out, sir?
Yes, ma'am.
Yeah.
Yes, ma'am.
So here. So here the function f of x is equal to 1 by x. Okay, so the domain is actually r minus z0 here. So the turning point, the domain, the idea of the domain they should have actually. There exists one point where the turning point is there in the graph. That idea they should have. So at that point, we have to encourage them to check the discontinuity, whether it is continuous or not continuous. Other points will not be a problem. So here, here limit extends to 0 minus the function 1 by x. If I am taking, it will go to a number which is, for example, 0 minus h. If I am taking limit h tends to 0, 1 by 0 minus h, it will go to minus infinity here.
Yes.
Because as h tends to 0, 1 by minus 0. It's actually minus 1 by 0. It will go to minus infinity. That is obvious from the graph also. That graph will go like this, isn't it? When it is approaching from the left side. Then right side limit extends to 0 plus 1 by x. So limit h tends to 0. 0 h method is always better. You can apply that because even if a question which is very difficult, h method will give you a proper solution. So x tends to 0, h will tend to 0. And here it is 0 plus h. and this value as h tends to 0 approaches to infinity. In this way, we can say left limit is not equal to the right limit. One is going to too small, another one is going to too big, and it is not, limit doesn't exist at that particular point, and so it is continuous. In that way, we can bring.
Yes, ma'am. Thank you.
The same will happen all these kind of questions. So when you introduce a problem, all these kind of problems at a stretch you introduce. Maybe 1 by x plus 1, 1 by 2x minus 1, 1 by x minus 15. All these kind of questions you give at the same time. So they will easily come to a conclusion. Okay, this will in the domain 5 is not there, because at a 5, 1 by 0 doesn't exist. So at the point x is equal to 5, they have to check the continuity. Here they have to check at the 1 by 2, they have to check the discontinuity. In that way, similar problem, similar to that kind you give. One problem you introduce, same type, different problems you give, they will understand it in a better way.
Okay, ma'am.
The same thing applicable to differentiation also. Similar kind of question give at the same time. Then what we face is the split problems, where there's two different functions, like it's there in the first exercise itself, lesser than or equal to 2x minus 3, x greater than 2. Here and all not a problem, because this is already a linear function. You can also show the graph of this one. So lesser than 2, exactly I don't know, maybe something it is reaching to one point, to the right side is going to somewhere else. So in that way you can give an idea about the diagram. Okay, and then you proceed at x is equal to 2. 2 is the turning point here. At that point only you have to check, you can say, because other points you take any point, it is a linear function. It will be definitely continuous only, because all linear functions are continuous. So as a particular case, this point alone, turning point alone you take, then we can check the continuity at that particular point. So you need not say everything here. Check the point of discontinuity when you are saying, check only at the turning points. Isn't it, teachers?
Okay, ma'am.
Any other doubts to discuss?
No, ma'am.
Okay, here I would like to give one horse question, which is from board itself, board question it is. Okay, so this is f of x is equal to sine of a plus 1 into x.
Yes.
Plus
That's what I
2
was telling.
sine x.
Yeah.
This question. Okay.
This question.
Yeah, this is divided by x when x is lesser than 0. It's a split function again. Okay, is equal to 2. And when x is greater than 0, it is root of 1 plus bx minus 1 divided by x. And this is given that it is continuous at x is equal to 0. And so find the value of the unknown number a and b. Small a and small b values we have to find out. So this was asked in 2016 in different question papers. Okay, so here also first thing you tell the children, f of 0 value right. Okay, f of 0 value is equal to 2. Immediately they are getting, and also encourage them to write the formula. So they immediately will get 1 mark over there. Okay, and then left limit extends to 0 minus f of x. Okay, 0 minus f of x will be limit extends to 0 minus, here let me write it directly here, because it's not a two different function. It is different function, not the same function. So I'm not using. Okay, I will use H method itself. Is it not compulsory, but not necessary, but I will use a plus 1 into x plus 2 sine x, the whole divided by x here. Okay, so this is limit extends to 0. We can split this into two terms, a plus 1 into x divided by x, and this is 2 sine x divided by x. Okay, and this will be, here they have to get all the limit formula on their head. We have to tell them repeatedly to learn that, and multiplying and dividing by a plus 1 here, a plus 1 here, they can bring the term like a sine theta by theta format. Isn't it, sir?
Yes, ma'am.
Yes.
Okay. So here they will be getting on applying the limit, they will be getting a plus 1 alone, because the rest of the terms will become 1. This term will become 1 here on applying the limit. Okay. And the sin x by x also will become 1 here and 2. In this way, we will reach the answer easily. Your H method will be slightly lengthier. So this is sufficient for this kind of question. Now, as a third point, limit extends to 0 plus f of x. So whenever this root type comes, we can immediately ask them or to tell them to start thinking the conjugate multiplication method. Okay, in order to simplify the question. Whenever this root type, root of a plus bx, this kind of question, we can encourage them to think like that. It may work, may not work in certain cases, but most of the cases it will work. So in this way we can tell, so limit extends to 0 plus. This is in the form of a plus b into a minus b, that the square root term will be removed. The denominator is not a problem because it is not giving you an indeterminate form. Then that 0 by 0 getting was the problem here. At each and every point, we should tell them to substitute and see, are you getting an indeterminate form 0 by 0 here? After changing the question, are we getting 0 by 0 form? Here you will not get 0 in the denominator. So it's ready to calculate the limit. That is how we tell them, okay, is it ready to calculate the limit or not? So here, one x I missed, sorry. And this x also will get a cancel, and b divided by root of 1 plus bx plus 1. Now, if you apply the limit as x tends to 0, we will be getting x value as a 0 here. If you substitute, we will be getting b divided by 2 we will get. And then if you say 2 is equal to a plus 3 is equal to b by 2, you will be able to calculate the value a and b.
Yeah.
So this was one of the important question. We definitely needed to give these kind of hot questions in the class. This one now we did more of actually continuity questions. Differentiability also we need to give like this. Okay. We need to encourage them to do. And some questions like this one, mode questions like this one. For example, this kind of question also asked in the board. F of x is equal to mod x minus 1 plus mod x plus 1. Okay, not differentiable at the point. I think for a last 2-3 years that lengthy question is not asked. For this objective only asked. In case the lengthy problem 3 mark, 4 mark and all, if they are asking, we needed to tell them to change the question. It's a better way to change the question and write it. Everybody knows that, right? I have to explain that? How to change the question?
Yeah. Yes.
So here I will show that also. This is a turning point that minus 1 and plus 1 for these two modulus functions. So we have to give the separate break we have to give and think what the function value of those points is. For example, if the x is at this particular point, that is x is lesser than minus 1, what will be this function value? This function value, it is lesser than the turning point, you have to give them first. So the modulus function question, always you give the idea in a very clear way. The turning point is at 1 here, and x plus 1 turning point is at minus 1. So here it is, sorry,
X plus 1.
X plus 1 when x is lesser than, sorry, x is x plus 1 is equal to 0, x equal to minus 1 is the turning point, right? So x greater than minus 1, this will be the positive value. Lesser than minus 1 case, it would be minus of x plus 1 in this way. So equality symbol you can include anywhere. That will not be a problem. So in this way, you have to give, and then each value you have to calculate. So lesser than x minus 1, first one will be like this, and the second function x plus 1 will be lesser than, it's still lesser than one case only. So it's minus of x minus 1. So altogether minus x minus 1 minus x plus 1. The finally 2x, you minus 2x we will get when x is lesser than minus 1. In this way, each case. Now, what happens when x is equal to minus 1? What happens when x is between minus 1 and plus 1? What happens when x is equal to 1? Like this, we have to separately define our functions, and then we have to, as usual, now it's a break question with the pieces. We can find out that already the first exercise they are learning, so they'll be able to understand. So give suggestions how to split this kind of question and make the question. This question is actually, we will get the answer like minus 2x below minus 1, 2 between these two, and 2x when it is greater than 1. In this way, you will reach the conclusion. So in that way, you have to work out. These are the different kinds of questions what I have noticed. Anything I have missed, sir?
No, madam. Yeah. So many examples we have given.